Hello, my name is Sean Bergen, and this presentation describes a portion of my dissertation research and has been recorded for the Comses Net Virtual Conference in the fall of 2017. The title of my talk is Neolithic Agropastoral Expansion, an evaluation of theoretical models using an agent-based model of the Neolithic spread in the Western Mediterranean. The spread and adoption of agriculture across Europe and the Mediterranean has been a focus of archaeological research almost as long as there have been archaeologists. Much of the debate has focused on who or what is doing the spreading. Are farmers arriving with their new agropastoral lifestyles and founding new agricultural settlements, or are indigenous hunter-gatherers adopting a new way of life? In the West Mediterranean, a little after 7000 BC, new food management strategies focused on domestic plants and animals spread rapidly across the West Mediterranean, traveling from Italy to Iberia and into North Africa. Researchers have put forth 4 hypotheses emphasizing the importance of population pressure, the arrival of new people, the role of indigenous people, or a combination of all of these factors. The focus of this presentation is the evaluation of these 4 main mechanisms of spread that have been proposed for the area using an agent-based model. The spread of the Neolithic in the West Mediterranean continues from 7000 to 4000 BC, and much of that expansion occurs within a few hundred years. In general, the Neolithic in this region typifies what is meant by the phrase Neolithic package. The first pottery known to the region is found in conjunction with the first evidence of domestic plants and animals, and new forms of domestic architecture. The Neolithic package first arrived on the Italian peninsula around or a little after 7000 BC in the southern region of Italy. The earliest dates are located in the region indicated by the red star. Arrows in this image represent the overall path as we know it that agriculture spread across the study area, and much of the area between the start and end points of these arrows have limited evidence of Neolithic settlement. In order to better understand and help evaluate the conceptual models of Neolithicization in the West Mediterranean, I have created an agent-based computer model, the Cardial Spread Model, which can be used to test and compare the 4 conceptual models of agricultural spread. The agent-based model is composed of forager agents and farmer agents, which exist upon a digitized representation of the West Mediterranean using the NetLogo platform. The 4 conceptual models of agricultural spread tested with this agent-based model are the Wave of Advance model, the Capillary model, the Maritime Pioneer Colonization model, and the Dual model. These models provide a series of testable, hypothetical mechanisms that are meant in some way to predict the rate and direction of Neolithic spread. If we were able to zoom in on the display in the previous window, we would see that the landscape is made up of square patches. Each square is equivalent to a 23-kilometer square area. Using published estimates of agricultural and forager land use, a carrying capacity is calculated for each patch. Each farmer agent represents an agropastoral village. It is located on one patch and has its own unique population. Forager agents represent a group of foragers, and unlike farmers, foragers may occupy multiple nearby patches simultaneously in order to represent a territory from which foragers would derive their resources. Each simulation begins with an agricultural village in southeastern Italy. Since very little is known or understood about forager populations at the time of agriculture's arrival, the simulation also begins with forager populations randomly located throughout the study area. The specific density of foragers in a simulation is a parameter that is tested in the experiments. The processes that occur in the model occur at an annual scale. During each year, the population of forager and farmer settlements changes based upon birth and death rates. After the population has been updated, agriculture may spread using the rules of one of the 4 conceptual models. The frequency, direction, and destination of such an event is determined by the spread model being tested. While there are certainly a number of important factors which are currently unknowable to researchers, this approach allows me to test different parameters and factors in order to better understand their impact upon the spread scenarios outlined in each conceptual model. In the cardial spread model, as each farmer agent chooses to where to move, it evaluates each possible new location based upon a land value assigned to that patch from an imported map. As a result, a variety of maps can be input as the deciding factor for an agent's evaluation of the land that surrounds it. Data from the CMIPS-5 Mid-Holocene Earth System Grid Paleoclimate Model, created by the U.S. National Center for Atmospheric Research, was used to create maps of prehistoric environmental conditions at 6000 BP. The CMIPS-5 model outputs maps of environmental variables, including precipitation and temperature on a monthly scale. To improve upon the resolution of these environmental maps, modern environmental data was used to downscale the core CMIPS paleoclimate model data. Difference maps were added back to the modern climate maps, which produced a set of high-resolution paleoclimate maps that vary appropriately for local topography. This process of downscaling was used to create maps of paleoenvironmental conditions that would have been beneficial for agriculture by combining maps of slope, precipitation, and temperature. For example, this map of wheat suitability was created by combining maps of slope, minimum temperature in March, maximum spring temperature in March, April, and May, and total spring precipitation. One of the most challenging aspects of using computational models in archaeology is making the results meaningful. The models I'm testing strongly emphasize the speed and spatial distribution of the Neolithic spread in the West Mediterranean. To evaluate the outcome of each simulation, each map of arrival times is compared to a map created from available radiocarbon data. The earliest arrival date of agriculture for 605 sites was used to create a chronological surface, or chronosurface. An interpolation routine in GraphGIS was used to fill in the space between sites. This map serves as a standard by which the results of each model run are judged. The maps are compared using a linear regression model in GraphGIS to describe the correlation between the two maps. This allows for an objective comparison between the chronosurface and model results output from NetLogo. I will now describe the results of some of these simulations. The results represent an aggregation of multiple runs and repetitions of runs that total just under 75,000 individual model runs, and a total of 3,747 distinct parameter combinations. The Wave of Advanced model emphasizes the importance of the reproductive benefit provided to practitioners of agriculture. The resulting population pressure upon the agropastoral village leads to geographic expansion as the group visions and new agricultural villages are established. The small-scale multiplication of villages leads to a macro-scale pattern best described as an outward wave of new settlements, which increases in geographic area as it extends outwards. In all these simulations, agriculture did not spread beyond the Italian peninsula in the allotted time, and the various paleoclimatic maps had a marginal effect on the correlation values with this spread type. As a result of the problems with the Wave Advanced model, a second and complementary conceptual spread model called leapfrog spread was also included. The leapfrog model is identical to the Wave Advanced model, except that farmers are able to move to non-contiguous locations. The best R value from these experiments was 0.48. Clearly, this is an improvement from the maximum correlation value recorded for the Wave Advance of 0.3. The best paleoenvironmental map is the map of slope, but they're all pretty close to one another. The capillary model stresses the importance of social networks for the spread of the Impresso-Cardial Neolithic. In this conceptual model, agriculture spread to foragers by way of network connections. Unlike the Wave of Advanced model, results from the capillary model usually occur too quickly. It's possible for agriculture to spread across the entire area in 400 years. Way too fast. Paleoenvironmental maps had little effect on the results, and 3 network configurations, one favoring close connections, one favoring far connections, and one randomly distributed, also produced no significant difference in the correlation values. Judged by the correlation values alone, the capillary model performs better than the Wave Advance, but not as well as the other model types. Nevertheless, it's impossible to discount this model without a firm grasp of the settlement distribution of indigenous groups. In the cardial spread model, indigenous groups were randomly distributed across the landscape, yet if many of the indigenous groups were located in a specific area, for example, coastal locations, the spread of agriculture in the model and the resulting correlation value may have been improved. The maritime pioneer colonization conceptual model emphasizes the importance of long-distance coastal movement to the spread of the Impresso-Cardial Neolithic. The best correlation value from this model was 0.52. The paleoenvironmental maps also had a marked impact with this conceptual model. The 2 paleoenvironmental maps with the highest correlations include rivers as a route for travel, and a similar pattern was identified with the dual model. Rivers weren't tested as transportation for the other models because they don't depend on maritime movement. The dual model attempts to integrate components of both the previous models by including maritime expansion by agriculturalists. The adoption of agriculture from forager and farmer interaction, as well as through down-the-line trade. The best simulation results from the dual model also resulted in a 0.52 correlation value. The paleoenvironmental maps also had a similar impact. While the best map was the slope and annual precipitation map, the second and third highest results also included a river for transportation and settlement. These experiments with the dual model spread underscore the importance of rivers as routes for transportation for early Neolithic movement. The highest correlation value from the dual model is almost identical to the best correlation achieved with the maritime pioneer colonization model. It's difficult, therefore, to decisively claim that one conceptual model of spread is better than the other. Overall, the maritime pioneer colonization model and the dual model have yielded the best results so far. The main difference between these two models and the others is the inclusion of coastal migration. I believe the relatively better success of these two models is a good indication that this is an important component of the spread of agriculture in this region. Obviously, getting the best correlation value from one spread type doesn't settle the debate about which conceptual model is correct. Ultimately, the purpose of this simulation is to explore and better understand these conceptual models, not necessarily declare one to be the best. In conclusion, the results from this agent-based model support the importance of long-distance movement, especially along waterways, to the spread of the Neolithic in the West Mediterranean. I'd like to thank Michael Barton, Marco Janssen, and Anik Kudar for their insights during the course of this project, as well as you for listening to this presentation. Thank you very much.